is pack learnable if an algorithm can, with high probability, output a hypothesis that has low generalization error. Okay? And this probably will not mean very much right now to you, but in the end of the course, end of this lecture, we'll go over it and review this sentence. This is very significant. Leslie Valiant, the professor, won the Turing Award. I hope you know what a Turing Award is. It's like a Nobel Prize given to computer scientists. Okay? And pack learning was for Leslie Valiant's contribution in introducing pack learning. He won the Turing Award. Okay, so you can see how important that this learning framework is. Okay, so let me just start off and look at a hypothetical problem. Here is papaya, and you want to determine which papaya is tasty and which is bitter. Okay? So that's sort of a machine learning problem. That can be. And in many cases, people look at the color and the smoothness of the papaya. Okay? And based on these two features, you determine whether the papaya is bitter or tasty. Okay? Now, you can think of two situations. This situation in the center, where the tasty papaya and the bitter papaya is completely separable by some ground truth function. Okay? So there is a boundary. Within this boundary, all the papayas are tasty. If you're outside this boundary, the papayas are bitter. This is one situation. And we call this the separable. The distribution of color and smoothness is separable. Okay? It's tasty and bitter. You can also consider this case where it's overlapping. The tasty and the bitter is overlapping. Okay? And we call this the non-separable distribution. Okay? So I want to ask you, what do you do? This is a completely different. So here, I'm trying to find this ground truth, and I'm going to get 0 training error. I'm going to get 0 test error as well. Here, it's impossible to get 0 test error. Okay? So when you have a problem, you have to think about this. Is it this situation or this situation? Okay? And I want to ask you right now, if you are in this region, where the color and the smoothness is this point right here, where you have some bitter and some tasty, what do? Can someone suggest an algorithm, or what would you do if you're right here? If you're, if you have this non-separable situation, you cannot get 100%. You cannot get 0 test error. You have to give up on that. It's impossible. Unless you look at another dimension where it is separable. If you're here and you're 80% bitter and 20% tasty, then you always choose bitter. And you're going to get 20% error. Okay? And you have to live with that. Okay? So just want to say that this is a separable, non-separable case. And in this case, this function is the target function. We call it the target function, or sometimes the concept, okay, that perfectly separates the classes given the feature X. Okay. Here in the non-separable case, you look at the joint probability of the feature and the label. Okay. And given this, you choose Y that maximizes this. Okay. Okay. So I'm going to consider the separable case today. Okay? The separable case today. And we're going to call this the realizable. So before I go into the theory of pack learning, I want to define some notations and give you some, introduce some words. Okay? Instant space. This is the set of all possible inputs. All possible inputs. The concept class is the set of all possible target function. Okay? And the hypothesis space is the function that you are trying to select. Well, it's a set of all functions that the learning algorithm can choose from. Okay? And this may be different from the target function. So the target function, as we saw in here, it's a very complicated function if we're considering this case, if we assume that this is this case. The hypothesis class is some function that we can sort of manage. For instance, squares that will approximate the target function. Okay? So to understand the difference between concept class and the hypothesis space. Okay? So it's square. Let's assume that it's going to be not a square, rectangle. Okay. The rectangle is defined by, a number of parameters, the corners, maybe the center and the diagonal, the width and the height. A number of parameters to define the rectangle, right? And I'm going to call those parameters theta. Theta will all include everything that defines that hypothesis. So this is one hypothesis. All the possible rectangles will lie in the hypothesis space. Okay. And I will have a learning algorithm to select the best possible hypotheses. Okay? It's a procedure that selects or constructs the hypotheses from the hypothesis space, and it's going to minimize some loss function. Okay? And generally, this loss function is a value between 0 and 1. Okay? It's bounded. Now, there's also a concept of inductive bias. Inductive bias is the set of assumptions or constraints that a learning algorithm imposes on the hypothesis space in order to generalize from finite training data. So you will be given not all the data in the world, but only samples. 10,000, 100,000. It's not all the possible training data, okay? And from that, you're going to use that to select the best possible hypotheses. Or you're going to construct the best possible hypotheses that will minimize the test error. Okay? And that hypothesis, the hypothesis class that you're considering, is not going to be a general function. It's going to be constrained. It's going to have some assumption. So in this example, the inductive bias is that it's going to be rectangle. Do you understand what I'm saying? The inductive bias is set by the hypothesis space. So if you're considering the separable case, there's going to be a target function that's not going to be rectangle, but this is too difficult to define. So I'm going to set a hypothesis space with some inductive bias. It's biased. It's going to be a rectangle. Okay? So understanding the word inductive bias. And then realizability assumptions. It states that the true target function lies within the hypothesis space. So if I have realizable assumption, then the hypothesis space will contain the true target function or the concept. But so the if this is a rectangle, then it's realizable. Okay? Today, I'm going to be talking about the realizable case. I'm going to assume it's realizable. I'm going to assume that it's separable. And I'm going to assume that the hypothesis space is finite. So if I'm talking about all the rectangles in this world, then it's not going to be a finite space. Okay? But rectangle in the digital space is going to be finite, right? But I'm going to assume that there's only going to be a finite number of hypotheses in the hypothesis space. Okay? You get all of this? These are some notations that I will be using. Yes?
Why the loss function has a bounded, for training the neural network, it does have the bounded, the decreasing on infinitely. But in this case, why does it have the bounded loss?
I'm just assuming that it's bounded. Okay? So I can make any loss function if I can make it bounded by dividing by the maximum value. So it's going to be less than 1. And usually the loss functions are always positive also. Okay? So I say 0 to 1 without loss of generality. Okay, I can always make it between 0 and 1. So these are some of the notations that I will be using, okay? And it will probably be very difficult for you to remember all of this, but I'll just go over it very quickly once and then I'll go over and over again. The feature space is going to be within this big X, okay? So the color and smoothness will be an element in this X, and Y is the classes, tasty and bitter. Or I could make tasty equal 1, bitter 0. Okay? And X and the product space, this product space is the domain space. And, so it's going to be, so I'm going to represent X and Y as Z, okay? And say that Z is, okay? I'm going to call S the training set. So I have M training set here, shown M training set. Oops, wait a minute, let me just erase this. Oops. I'm going to denote this as a particular instance in the training set. Okay. I'm going to denote D as the distribution. Oh, here it is. I'm going to denote D as the distribution over either x or z. F theta is the function, the hypothesis, which is parameterized by theta. Okay. So if it's parameterized by theta, the learning algorithm will try to find the particular theta that would minimize the test error. F without the subscript will be the concept or the target function. LS will be the training error. Okay. Looking at the training set, set S. This notation, LDF, will be the test error based on the concept F. So I'm assuming that it's separable with the concept F, and the data is distributed by distribution D. Okay? LD is the test error. It's just a test error based on the distribution D, and there's no F in this thing. So this is test error for the non-separable case. H would denote the hypotheses. It's a set or a basket full of all the hypotheses that you will choose from. HB, I'm going to be talking about this bad hypotheses. B stands for bad, meaning that it's hypotheses that would give test error greater than epsilon. And epsilon is any value that you care to choose. One minus delta. Delta and epsilon are values between 0 and 1. 1 minus delta represents the confidence. It's just confidence, okay? And epsilon is the accuracy. Okay. I know this is difficult for you to remember. I'm going to go over and over again, okay? And please ask me if you don't remember a certain notation, okay? And I'm going to assume that the training data is IID, meaning that each of the training samples or examples are independent, meaning that one sample does not depend on the other sample, and they're all identically distributed. They all come from distribution D. Okay? So if I assume that, and my training set comes from a distribution, m-dimensional distribution. It's an m-dimensional because S is M training set. Each one is independent, of course, but if you can generalize this and say it's somehow dependent, then I'm looking at an m-dimensional space. M-dimensional probability space, and I'm going to denote that as dm. Okay? But I've assumed IID, so that distribution is a product of individual distribution, individual probability distribution of m things. Okay? This comes from IID. The training error is sometimes called the empirical risk. Okay? And the training error is denoted this way. You're given input xi feature. This is the ith feature. And it will have ground truth label yi. Your function is going to take xi and make a prediction on the label. And it's going to compare with yi and give you a loss. This loss is generally a value between 0 and 1. And in the training sample, I have m examples. So this is the sum of all loss. And I'm going to divide by m over 1, so that's the average loss. Okay? And we call this the training error for the hypothesis f theta. Okay? The objective in machine learning is, of course, to minimize the test error or just the risk. And if we're talking about the separable case, where there is a true concept or a target function, then it's the expected loss. The expected loss is the risk. Okay? And the expectation is over all the instances. Okay? This is the separable case. If it's non-separable, then x and y are random. Okay? So for a particular x, y could be bitter and it could also be tasty. So I'm going to do this loss over the expectation of the joint probability. And sometimes you can write it like this. This is if you have lots of mathematical maturity. The loss of the hypotheses that you are considering and the data, which is lying in the xy space. It means the same thing. Okay? Please ask questions if you're confused by something. Empirical risk minimization. It's a learning algorithm. It's one of the most simple learning algorithm. What is it? It returns a hypothesis that minimizes the training error. Okay? So you look at all possible theta in your hypotheses, and you look for theta that minimizes the training error. That is ERM. Looking at the hypothesis H given the training sample set. Okay, and we denote that as FS. This may not give you the smallest risk. Okay? Now I'm going to be talking about 0-1 loss quite often. 0-1 loss is when the prediction equals ground truth, then the loss is 0. When they're different, the loss is 1. Okay, it's simple as that. 0-1 loss. The second fact I mentioned, the hypothesis represents the inductive bias. Okay? The ground truth or the concept is very complicated, but I'm going to look at only the squares or the rectangles. That is an inductive bias. I'm assuming, I'm placing a bias. Okay? ERM can overfit. I mentioned what overfitting was in my previous lecture. Overfitting is a situation where you have low training error but high test error. There's a discrepancy. Practice, you do well, but in the exam, you do badly. Okay? ERM can give you overfitting because ERM is just focused on minimizing the training error. Okay? If we assume that the training error is 0, we can have training error equals 0, but the test error being a half. This is probably the worst error. How would you have test error that is 1? You always have to be the opposite. So that means you have a lot of knowledge. 1/2 is random. Okay? So this is a particular case of ERM where it's 0 training error. What is if the input that you have, X, equals one of the training sample, then you output the label of the training sample, of that training sample. Otherwise, you just set it to 0. Or you could just set it to 1. This one has 0 training error, right? It's going to get the training error perfect. It's going to get the training samples perfectly correct. But the test is going to be, for the test, for data that it hasn't seen, it's going to be half right and half incorrect. If the probability of 0 and 1 are balanced. If you have half and half. Okay? Okay. This is what we're going to work on. Statement like this throughout maybe first half of the course. Okay? So let's look at machine learning situation. We have training data. From that training data, we somehow try to minimize the training loss. And we hope that minimizing the training loss, we do well on the test data. So we hope there is some relationship between training error and test error. That's a hope. If the training data sample is infinite, if it's all, then the training error and the test error are going to be the same. If we have infinite number of data, but we don't have infinite. We only have finite number of data. So we ask ourselves, how many training data do we need so that the training error, minimizing the training error, will also lead to minimizing the test error? Do you understand this situation? Okay. So let's look at this statement right here. I'm given M training data, and I'm going to use an algorithm called ERM to select the hypotheses from the hypothesis space. That's minimizing the training error. And that hypothesis is going to be f of s. Okay? That's how I select that hypothesis. Then I'm going to look at the test error using this hypothesis. And let's assume that that test error is less than or equal to epsilon. This is achieved by the training set. If I have a lot of training set, if I have many training set, then this could probably be achieved. And I want to look at the probability of this happening Okay? So this, you can see that ERM, I choose ERM, then I look at the test error. Okay? I want to see the probability of that test error being less than epsilon. And that would depend on the sample. So there are infinite number of samples, and I'm going to choose some m number of training set, and I'm going to use that training set to get my f of s, and then I'm going to look at the test error and see, whether that's going to be less than epsilon. And I want to look at the probability of that. It depends on how I select the training set. And I want that probability to be greater than 1 minus delta. If delta is small, let's say 0.1, 90% of the time, so I choose training set like this, and then I get my f of s, I look at the test error, 90% of the time, it's going to be less than epsilon. That's what this statement is saying. Okay? And so this is a good statement, okay? Because this links training data, algorithm, test error, bounded, the probability with this confidence. And it's all random because, sometimes your training set is lousy. Okay? But I want that probability to be low. So in order to achieve this, what is the condition? What is the condition for achieving this? Thank you. IID? So if I have two IID data, you think I can achieve this for all the cases?
Training sample should be high enough to generalize all the samples data.
Right. I need to have a lot of training data. As I said before, if I have infinite number of training data, infinite number of training data, then it's the equal as the test data, test situation. And I choose I use my ERM, and if the training error is less than epsilon, then the test error is going to be less than epsilon. Right? That's for sure. So, the condition will be, how many samples do I need to achieve this? How many samples do I need? That's a very important question, okay? And what I'm going to do for today, I'm going to assume the realizable case. Realizable case. What is realizable? The concept or the target function is in the hypothesis space. So the function that I select by using some ERM can be the target function, the actual target function. Do you understand what I'm saying? But the example that I showed you in this, if the target function, I'm assuming a lot of things. I'm talking about separable case, okay? But generally it's non-separable. I'm assuming it's separable. The target function looks like that. In general, but I'm saying that the concept, the target function, is a square. That's the realizable case. Are we all done? Oh, 20분. Okay. So I'm going to assume the realizable case. Okay? And I'm not going to deal with the general case where it's non-separable. Now I'm going to be talking about pack learning. Probably almost correct. This is almost correct. And it's probable. Probably almost correct. I'm not looking at 0, I'm looking at less than epsilon. So, realizable assumption mathematically, usually ground truth or the concept is in the hypothesis space. That's realizable case, such that the test error is equal to 0. If you choose ground truth, then you're going to get all of them right. And it turns out that with probability of almost 1, probability of 1, the training error will always be 0 as well. Probability of 1. What does it mean by probability of 1? I want to give you this. Let's say it's a real number. You have x is real number. What's the probability that you pick a number 2? What's the probability of 2? So the x, the domain, x is a real number. Okay? So you have a distribution of the real numbers. What's the probability of x equals 2? 0, that's what I'm saying. There are rare cases where the training error is not 0. Particular rare cases. But if you over some range, it's 0. So there are rare cases where this is not true. But almost all, it's okay. That's what it means by probability 1. So by ERM, you find this hypothesis and you apply it on a finite training sample, M training sample. The training error is going to be 0. Okay? This and this are like sort of different things. This is averaged over all possible outcome. This is only some particular set. And with probability 1, Only on very rare cases, it's not, the training error is not 0, but almost all cases it's 0. That's what probability 1 means. Okay? So this is saying, this is basically this. I was looking at this definition. What is the probability that I pick out some M training set such that if I perform ERM and get my f of s, the test error in this statement is greater than epsilon? So I was looking at some other cases where it was less than epsilon, and I wanted that the confidence of that to be greater than 1 minus delta. What should it be here in terms of delta? Smaller than delta. It's the same statement, but saying it in a different way. The opposite thing, okay? And I want to bound it by 3 things. The number of samples. Number of samples. M is the number of samples. I don't know if you've seen this notation before. This is called the cardinality of the hypothesis space. Cardinality means how many elements are there in the hypothesis space. How many hypotheses are we considering? Okay. Generally, the hypothesis space, the number of hypotheses you are considering is infinite. It's not finite. But we're going to assume that there are a finite number of them. But of course, if you're looking at the digital space, then because all the numbers are, in bits, so that it's going to be finite. But anyways, that's cardinality of the hypothesis space. And it's going to also depend on epsilon, on this value right here. So if epsilon is high, a big number, epsilon is between 0 and 1, by the way. If it's closer to 1, would you need more samples or less samples?
Less.
If this is, let's say I'm comparing between 0.5 and let's say 0.1 and 0.9. If I want this to be greater than 0.9 or 0.1, which do I need more which one requires more samples? 0.1, epsilon being 0.1 and 0.9. Test error being greater than 0.9, test error greater than 0.1. For 0.1, I would need less samples. Is that right? Okay. Anyhow, so now I'm going to define bad hypotheses and misleading hypotheses. So the bad hypotheses are, so this set is a set of hypotheses. Okay? And the hypotheses in this space, in this set, will have test error greater than epsilon. Okay, so epsilon, if it's greater than epsilon, it's bad. If it's less than epsilon, then it's good. Okay? And epsilon is something that you can, you can arbitrarily set. So this is a bad hypothesis. It's always giving you test error. Misleading samples. So this is a set of samples. This is a set of hypotheses. This is a set of samples, data. And what is it? It's training samples, okay, such that it gives you an ERM, FS, and the test error is greater than epsilon. So it's misleading. Why is that misleading? We're considering realizable case. What is the minimum training error that you can get in the realizable case? 0. Okay? So the training error is 0. So for all M tuples, any M training set, it's possible there is a hypothesis that will give you 0 training error. You choose it. And that's f of s. It looks good on training, on training data. But the test error is greater than epsilon. So it's misleading. It's misleading. And this is a set on the hypothesis. It's a set on the training set. Okay, the start is the training set. And we call that, M, okay? So we can also write it like this. We can also write it like this. There is an element in the bad hypotheses where if you look at the training error on this particular, on certain sample, it's going to equal to 0. Okay? And I'll show you this pictorially. So here is the samples of M tuples. Okay, so each point represents M training set. Okay, there's M training data in any one of these things. Okay. This here represents hypothesis space. So the points here represents all the possible hypotheses. Okay? This region represents, all the elements in this region represents hypotheses that will give you test error greater than epsilon. So these are bad hypotheses. All the hypotheses outside can give you test error less than epsilon. So these are, okay? I could take an element or a hypothesis in the bad hypothesis set. It's going to give you a test error greater than epsilon. And I could find a training set, training data, which will give me training error equal to 0. Right? From all of this, I can find this function. I can find an M training data, M training set that will give me 0 training error. Okay? And of course, I'm talking about realizable case. And it's possible that 2 different hypotheses in the bad set lead to a common training set that will give you 0 training error. Okay? And this would be misleading because training error is 0. Oh, you think it's good, but it maps to a function that is bad. Okay? So it's possible that 2 hypotheses here lead to a common training set that gives you training error equals 0. You can have a hypothesis that's not shared by other hypotheses, okay, misleading, but the training error is equal to 0. You can also find a hypothesis that does not, if you put in, you can put in all the training set and it's not going to give you 0 training error. So there's no corresponding training M set where the training error is equal to 0. Okay? Does that make sense to you? So these represents all the possible things. Okay, going backwards to misleading. If we assume that it's realizable, then all the M training set will be 0 if you apply it to the concept or the target function. H star. It will give you 0. Right? So all the points here, M will be 0 when you apply it to H star. Right? That was the assumption about realizable. Okay? So for a function like here, S3, there are M training set. If you apply it to H star, it's going to give you 0. It's also possible that if you apply it to this function, it also gives you 0. You could have multiple hypotheses that give you 0 training error. Okay? Everyone understand this graph? Here is sample. Here is the hypothesis space. I'm going from here to there. Okay? And then from here to there. Now, so this is HB, this is misleading. Misleading set can be defined by going into the bad hypothesis set and then looking for training set that gives you zero training error. So for each hypothesis in the HB, for each of them, you look at the training error and see whether it gives you zero. You look at it's the union of all the m-tuple training set that gives you zero. And you apply the bad hypothesis. Okay? And it turns out, okay, the ERM, so let's say for this one, ERM it's possible that it could choose the red one or the black one, right? The ERM, because the training error is zero for both of them. But if you choose this one, the black one, then the test error is greater than epsilon. If you choose the red one, then the test error is equal to zero. You don't know because you only have M training there. Okay? So it turns out this set, it's a set of all the S's. You apply your ERM, which gives you epsilon, which gives you test error greater than epsilon. It's going to be smaller than the misleading complete set. So this one is defined by going from here to there. That's this whole thing. But going from here to there, because they are the training error is both zeros, you could be, you flip a coin in choosing one. If you choose the red one here, then this S2 would not be in this thing right here. If, for S1, it's possible that it could choose that one, that one, that one. And let's say by chance it's choosing H star, then S1 would not be in here. So it's a subset of big M. You understand what I'm saying? Now, I'm going to put probability over these two sets. And what I really want is, I want to achieve this one right here. Okay, that was my goal. Okay, as I said, ERM, the test error being greater than epsilon, and I want that probability to be greater than 1 minus delta. What is the condition for this? How many, it's going to turn out, how many training errors do I need for that? So I had this situation, okay? I'm going to put probability on both sides. dm is probability. Now the probability of the union is upper bounded by the probability of the individual, right? Probability of the union of A and B is upper bounded by the probability of each individual. So that's there. That. Okay. Now we also said that because the samples are independent, we can write it as a product. Each one if it's classifying correct, if it's the concept for these samples, that is 1 minus the test error for each individual. You write it like that. And we said that we wanted the test error of this to be greater than epsilon. So this is going to be upper bounded by that coming down here, and this one up. One of that, sorry. Well, this one is less than epsilon, so that's 1 minus epsilon. There are n number of them. And now it turns out 1 minus x is upper bounded by e to the minus x. So I can switch this and make it into e to the minus and that. And so how many HBs are there? This is independent of F. So I could, this is upper bounded by the number of bad hypotheses times e to the minus m. This number is smaller than the total number of hypotheses. And I want this number to be upper bounded by that number. And I want that to be less than delta. Okay. So from this, and this is saying, in order to satisfy that condition, I need to have training samples that are greater than this. So let's have a look at this and just review this. I wanted the test error to be greater than or less than epsilon, okay? And I wanted that probability to be greater than 1 minus delta, right? That's the delta here, and this is the number of samples here. Now, if epsilon is small, if I wanted my test error to be less than epsilon, and epsilon is getting smaller, do you think I need more samples for that? That's a much harder problem. So if this is smaller, then this is going to be bigger. I need more samples. Now, for the same epsilon, I want the confidence to be greater. I want it to happen more often. That means that delta has to be smaller. So if I wanted a higher confidence, delta has to be smaller, which means that I need more samples. And if there are more hypotheses to select from in the hypotheses, then I need more samples. You can think otherwise. So this is path learning. Okay. Given the confidence of 1 minus delta and accuracy of epsilon, where epsilon and delta are between 0 and 1, and I'm assuming 0-1 loss. I've been assuming 0-1 loss throughout. So the loss, the training error is going to be between 0 and 1. The training error is the average of the training set. Test error is the average of all the possible training sets. Okay. I've assumed realization meaning that the target function is in the hypothesis space. So the test error could be 0 and the training error could be 0. I assumed finite hypothesis space. Okay. So in order to satisfy that, I need this many. It needs to be satisfied. I need this many samples. This is, if I rearrange this, this is going to be the same as this. Okay. So I'm going to stop right here, and there are questions. Okay, so this is what understanding this. ERM, realization, realizability, ERM, test error being less than epsilon, that probability being greater than 1 minus delta. This is called the confidence. This is the accuracy. In order to achieve that, how many samples do I need? Okay. So I'm done here. Questions? And then what I'm going to do is I'm going to try to remove, these assumptions, realizability assumptions. I'm going to try to remove finite number of hypotheses, because in reality, I have infinite number of hypotheses. So okay. Think about it, and think about questions. You put it up on the board, and I'll see you Wednesday. Okay. Good.